Hi everyone, Dr. Burns here with our second lesson in Chapter 6, Representing Molecules. And in this lesson, we are going to learn about our Lewis structures and formal charge, as well as some of our exceptions to the octet rule. So we've learned about Lewis structures and we've mastered drawing those Lewis structures utilizing our guidelines from our previous lesson. So now we have to think about formal charge. Now, formal charge can be used to determine the most plausible Lewis structure when more than one possibility exists for a compound. So if you think back to our previous lesson, we talked about a structure that looked like this. We had C, O, and S. And we started off our structure where we had lone pairs all along our oxygen and our sulfur, and we had to make some double bonds in order to make our octet on our carbon. In our lesson, I said that we were going to take one lone pair from the oxygen and one lone pair from the sulfur in order to make our final structure of C double bond O double bond S with two lone pairs on the oxygen and the sulfur. Now what we could have done is we actually could have, instead of taking one lone pair from the sulfur, we could have taken another lone pair from the oxygen and formed a triple bond. So another version of this structure would be sulfur with a single bond to carbon and all of its lone pairs, and then a triple bond from the carbon to the oxygen with just one lone pair on the oxygen. We can see from this structure that our octet rule is still followed for our carbon as well as for our oxygen, but this is just another structure for that compound. Along with that, we could have also decided to not even take any of the lone pairs from the oxygen and instead take both of them from the sulfur. Meaning we could also have the structure with a sulfur triple bonded to a carbon, single bonded to an oxygen with its lone pairs, leaving just one lone pair on the sulfur. So all three of these structures are all plausible structures for that Lewis structure. So our formal charge says that we can utilize it to determine the most plausible Lewis structure when more than one possibility exists for a compound. So we can use formal charge to tell us which one of these structures is going to be the most preferred. To calculate formal charge, we have to take the difference of our valence electrons of our individual atoms and subtract off its associated electrons. Now we've talked about valence electrons before, and we know how to find those from our periodic table and our group numbers. But associated electrons are those that are wrapped up in either non-bonding electrons or bonding electrons. So our associated electrons down here are categorized as the number of non-bonding electrons, aka lone pairs, as well as half of the atom's bonding electrons, which would be our bonding pairs. Okay, so the lone pairs, these are the ones that are localized on the individual element. And the bonded pairs are the ones that are shared. Now we say that this is half, we only consider half of these bonded pairs because one electron came from one atom and one electron came from the other. Sorry, my handwriting is not great right there, but one electron came from one atom and the other electron came from the other atom. So only one, so the, oh. So the formal charge of the individual atom only considers the one electron that it gave to the bond being formed. Okay, let's practice using this. So let's look at the structure O3. This is called ozone, like what's in our atmosphere. Ozone, O3. Okay, so for each oxygen, what we're going to use is we are going to take our number of valence electrons and subtract off our number of associated. And that's going to give us our formal charge. And we're going to make sure we keep our signs as is, because that's going to tell us if the charge is either positive or negative. So we're not going to worry about if a number comes out negative, should we make it positive? We're just going to keep it negative. We're just going to do our math as is. So for each oxygen, for each of these oxygens, we know that each oxygen has 6 valence electrons. So here's our calculation down here for formal charge. Okay, so it starts off with their 6 valence electrons. We know that oxygen has 6 valence electrons because it's in group 6A. We next have to determine the number of associated electrons. So our associated electrons are the number of lone pair electrons. So we have to count each electron in those pairs. So let's look at our leftmost oxygen first. In this oxygen, I have 4 electrons that are in lone pairs. So those would be my 4 non-bonding electrons. And to that number, we have to add our associated electrons that are in bonding, but we take half of the number of electrons that are in bonds. So this oxygen has 2 bonds to it, right? It has a double bond there. Each double bond, or each bond in that has 2 electrons, so the double bond overall has 4 electrons, but only 2 of those electrons came from that oxygen, so that's why we divide that by 2. So this oxygen overall has 6 associated electrons. You could also see this number, instead of taking the number of bonding electrons and dividing by 2, you could also see this as just the number of bonds and not even worry about dividing by 2. That's also a way that you can, that some textbooks and some videos online present formal charge, is they just say it's the number of lone pairs minus the number of bonds. You could also do that as well. Okay, so because this one has 4 electrons wrapped up in a double bond, we divide 4 by 2, so we get 2. Again, just like it has 2 bonds, so we take 4 plus 2. That gives us 6 electrons that are associated with that oxygen. So for this electron here, I'm going to try to draw a line to show that that's for the leftmost oxygen. We take our valence electron 6, and we subtract off the number of associated electrons for that oxygen, which we just determined as 6. Therefore, the formal charge for this individual oxygen is 0. So when we're finding formal charge, we're finding it for each individual atom in the molecule. Okay, let's do another one. I'll erase this so it's a little less confusing while we focus on another oxygen, because its number of associated electrons are going to change. What's not going to change is the number of valence electrons. That oxygen, our second oxygen here, okay, it's also going to have 6 valence electrons. Okay, so we know that oxygen will always have 6 valence electrons. So we always know our first number in our calculation for formal charge. We now have to determine the number of associated electrons. So in this oxygen, there are 2 electrons in a lone pair. So that's the 2 unshared electrons. In this oxygen, there's 3 bonds to the oxygen. So if there's 3 bonds, that means 6 electrons are wrapped up in bonds on that oxygen. Therefore, we take 6 and divide it by 2, which is shown here, which is 3. So 2 plus 3 is 5 electrons that are associated with that oxygen. So we take that value and we now subtract it. We take 5 and subtract it from our number of valence electrons. So 6 minus 5 is plus 1. So the formal charge on this oxygen is now plus 1. We can see the difference between our first oxygen here and our second oxygen here. This first oxygen had a formal charge of 0. Their formal charge is going to be different because this oxygen, the one on the left, has 2 bonds and 2 lone pairs, whereas the oxygen in the middle has 1 lone pair and 3 bonds. So because they have different bonding schemes and different number of lone pairs, that means their formal charge is going to be different. If we had another oxygen that had 2 bonds and 2 lone pairs, then it would have the same formal charge as that oxygen there. Okay, so let's now work on our last oxygen. Again, just erasing here. Okay, so let's look at our rightmost oxygen. We know the formal charge is going to be different from our previous 2 because this oxygen now has 1 bond and 3 lone pairs. So it's not going to have a formal charge of 0 and it's not going to have a formal charge of plus 1. So let's determine what its charge is going to be. Well, this oxygen, we're going to count up our unshared electrons first, our number of electrons in lone pairs. So that's going to be 1, 2, 3, 4, 5, 6. So we have 6 electrons that are unshared that are in lone pairs. Then in this oxygen we have 1 bond. Because there's 1 bond, that means there's 2 electrons that are being shared. This oxygen can only claim 1 of those electrons, so that's why we divide it by 2. So 2 divided by 2 becomes 1. 6 plus 1 is 7 electrons that are associated with that oxygen. So we take that 7 and we plug it in as our associated electrons. So 6 minus 7 is -1. And this is where we want to make sure that we're getting our charges right. Okay, we always want to make sure we're subtracting valence minus associated so we get the proper charge, okay, the proper sign. So this oxygen has a formal charge of -1. Okay, so each of these oxygens has a different number of associated electrons, which we see here, because they have different numbers of bonds and lone pairs associated with them. So they have different formal charges. Overall, we can take these formal charges and sum them together. We take 0 plus 1 minus 1, and we get an overall formal charge of 0, which is the overall formal charge, which we also see on our molecule here. O3 doesn't have a charge on it. If we have a charge on the atom, then we should have an overall formal charge that equals the charge on that molecule. So let's do a few more examples of this, because again, just like our Lewis structures and what we were doing in our previous lessons, it's all best learned through practice. So let's practice assigning our formal charges for NF3 and ClO3-. So when we're looking at NF3, we're going to draw our Lewis structure first, and we're going to follow the same rules that we did for Lewis structures in our previous lessons. Our first step tells us that we have to count up our valence electrons for all of the atoms in our molecule. So nitrogen has 5 valence electrons because it's in group 5. Fluorine, there's 3 of them, and they each have 7 valence electrons that they contribute to bonding because it's in group 7A. So in total we have 26 electrons to put into this molecule. Okay, so we then draw our skeletal structure with nitrogen in the center, and fluorines are 3 fluorines all around it, and we attach it to our central atom using bonds. So in each bond there's 2 electrons. I used 6 electrons to make my 3 bonds, so I'm going to subtract off my 6 electrons, and I have 20 electrons left. We're next going to use those 20 electrons to complete our octets for all of our fluorines. Our fluorines currently only have 2 electrons associated with them, so they need 6 more. So we're going to put those on as lone pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I used 18 electrons to complete my octet for all of my fluorines, which means I have 2 electrons left. Those 2 electrons are going to go on my nitrogen so that we can complete its octet. Before I added those lone pairs, it only had 6 electrons around it. It needed 2 more, so those 2 electrons were happy to go on that nitrogen to complete its octet. So that's our structure for our NF3. We now want to assign the formal charge for all of the atoms in it. Luckily for us, all of these fluorines are identical, so we just need to find the formal charge of nitrogen and fluorine, and 1 fluorine. We only need to look at 1 because what we do for 1 can be applied to all of the fluorines since they all look the same. Okay, so I personally like to draw these as I attach them to the individual atoms, so I like to do this. That's just how I've learned to draw it. If you want to draw it on a little table or on the side, you're more than welcome to do that, however way you best see formal charge, and as we're learning this, do what works best for you. So remember, our equation for formal charge is number of valence electrons minus our number of associated, where number of associated is number of unshared electrons plus the number of shared divided by 2, which you could also see as just the number of bonds. So you could do that as well. Either works. Okay, so first, nitrogen. Nitrogen has 5 valence electrons. We already knew that from counting our valence electrons to draw our Lewis structure. So we're going to take 5 valence. And now we're going to subtract off our associated electrons. So how many unshared electrons are there on this nitrogen? Well, I have a lone pair. That's not being shared. So 1 lone pair has 2 electrons. So I'm going to subtract off 2 electrons from my lone pair. And next up, I'm going to subtract off my number of shared electrons divided by 2. So nitrogen has 1, 2, 3, 4, 5, 6 electrons. And I'm going to divide that by 2. So 6 electrons in bonds, which we're going to divide by 2. So we know 6 divided by 2 is going to be equal to 3. Okay, we can simplify that to 3. You could also see this as it has 1, 2, 3 bonds. So we take 5 and we subtract off our 2 electrons from lone pairs, our 3 electrons that are shared in bonds, and we get a total charge of 0 for nitrogen. Okay, so let's next up do fluorine. Fluorine has 7 valence electrons. Okay, we knew that from when we counted in the beginning of this to draw our Lewis structure. We now want to subtract off our number of electrons that are unshared, so minus how many electrons are in lone pairs. Each fluorine has 1, 2, 3, 4, 5, 6 electrons, so we're going to subtract off 6 electrons from lone pairs. And then each fluorine has 1 bond, each bond has 2 electrons, so we're going to subtract off 2 electrons from bonds, but divide that value by 2, which we can simplify to 1, right? 2 over 2, 2 divided by 2 is 1. You could also see that as each fluorine has 1 bond. So in total, we take 7 minus 6 minus 1, so that's in total a 0. We subtracted off all 7. So 0 charge for fluorine. So if each of my fluorines has a charge of 0 and my nitrogen has a charge of 0, my total charge overall is 0. And our NF3 that we looked at in the beginning here doesn't have a charge, so our formal charge adds up correctly. Your charge, the sum of your formal charges, should equal the charge on your molecule. Okay, let's try another one. For space purposes, I am going to have to erase what I have on here for the screen. So if you need to review this really quick, feel free to pause the video before I remove it, just to follow my work. Okay, so next up we're going to do ClO3 minus. So we're going to do ClO3 minus. So first step of our drawing Lewis structures is count up our valence. So chlorine has 7. For oxygen, there's 3 of them, and each oxygen has 6 valence. And because this has a charge of -1, we have to add 1 extra electron. So in total, I have 26 electrons to work with in this structure. Chlorine is our central atom, and it's going to be bonded to the 3 oxygens. So in making those bonds, I used up 6 electrons, leaving me with 20 electrons left over. I'm going to use those 20 electrons to distribute as lone pairs to complete my octets on my surrounding atoms, so my oxygen. So each oxygen currently has 2 electrons, 1 bond, okay? So they all need 6 more electrons. So we do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I used up 18 electrons to complete my octets of oxygens. I now have 2 electrons left over, which I'm going to put on my central chlorine to complete its octet. Okay, so I used up all my 2 electrons. I'm going to just denote my charge with a small bracket up here to remind myself that I have a charge of -1 in my structure. And now we can jump into finding our formal charge. I would like to note that you need to have Lewis structures mastered in order to accurately complete your formal charge calculations, because if you're missing lone pairs or have too many bonds or have double bonds when you don't need them, it is going to change your values of formal charge. And if your formal charge doesn't add up to the charge on the molecule overall, then something is wrong, either in your calculation or in your structure. So first make sure that your Lewis structure is correct, and then move on to your formal charge. Okay, so lucky for us, each oxygen is all the same, so we just have to find the formal charge for one of them, because what I do for one can then apply to all of them. I don't have any oxygens that are different. Okay, so let's look at our oxygens first. Oxygen has 6 valence electrons. That's our first step. We have to find our number of valence electrons. Each oxygen is going to have 6 valence electrons. We're now going to subtract off all of our associated electrons. So our unshared electrons are the lone pairs. So there's 1, 2, 3, 4, 5, 6 electrons in my lone pairs. I have 3 lone pairs. Therefore, I have 6 electrons that are unshared. So I'm going to subtract off my 6 electrons from lone pairs. And then I'm going to take my number of shared electrons and divide it by 2. Each oxygen has 1 bond, which has 2 electrons. So we're going to subtract off 2 electrons from bonds and divide that by 2, since the oxygen can only claim one of the 2 electrons. So 2 divided by 2 cancels out to 1. So we take 6 minus 1, and that gives us a formal charge for the oxygen of -1. So each oxygen has a charge of -1, -1, and -1. They're all the same. They all have 1 bond and 3 lone pairs, so they all have the same formal charge. Your calculation would be the same there. So let's now do our chlorine. Okay. Chlorine has 7 valence electrons. Okay, we know that from the periodic table. And now we're going to subtract off our associated electrons. Well, it has 2 electrons that are in lone pairs, so we're going to subtract off 2 electrons to account for our lone pairs. And now we're going to subtract off our shared electrons. So the chlorine has 1, 2, 3, 4, 5, 6 electrons that are in bonds. Which we're going to divide by 2 because it can only claim one of each of those electrons from each bond. So this simplifies to 3. So we have 7 minus 2 minus 3, so that would be 7 minus 5, which is a charge of +2. So that means my chlorine has a charge of +2. If we take the sum of all of these, if we do -1 plus -1 plus -1 plus +2, we get an overall charge of -1. And if we look back to our structure, it also has a charge of -1. So our formal charge equals out to the charge on our atom, or our molecule, so we know that we are correct. Okay, let's keep practicing. These questions are coming from your ALEKS homework, so you'll see similar problems when you finish this lesson and go to complete your homework for the week. Okay, so for each of these, a student is proposing the Lewis structure for the given molecule. What we want to do is just assign the formal charge to each atom in the student's Lewis structure. Okay, so we're going to find each atom's formal charge. So let's start with N. We're going to label our N's 1 and 2 just so we know the difference. They are not the same, right? This nitrogen has 1 lone pair and 3 bonds, whereas the other nitrogen has 3 lone pairs and 1 bond, so their formal charge is going to be different. So we want to make sure that we are calculating for the correct nitrogen. So let's do nitrogen 1. Okay, nitrogen 1 has 5 valence electrons. Thinking about oxygen from our last problem. Nitrogen has 5 valence electrons. We're going to subtract from that our associated electrons. So it has 1, 2 electrons. Let me zoom in so we can see that structure a little bit closer up. We have 1, 2 electrons in lone pairs. And then for our number of bonded electrons, well, this nitrogen has 1, 2, 3, 4, 5, 6 electrons from bonds, which we're going to divide by 2 because they're being shared. So that simplifies to 3. So we have 5 minus 2 minus 3, which is an overall charge of 0. So this nitrogen's formal charge is 0. Let's next look at the oxygen. So oxygen, we know, has 6 valence electrons. That's from the periodic table. For our associated electrons, the oxygen doesn't have any lone pairs on it. It only has bonds, so minus 0 from lone pairs. You don't even have to write it, but I'm choosing to write it just to remind myself that I've accounted for them since there aren't any. Okay, so minus 0 because there's no lone pairs. And then for bonds, it has 1, 2, 3, 4, 5, 6, 7, 8 electrons that are wrapped up in bonds, so minus 8 electrons from bonds, which we are going to divide by 2, which we can simplify then to 4. So we have 6 minus 0 minus 4, so that gives us a charge of plus 2. So that oxygen has a formal charge of plus 2. Okay, we now have N2 here. N2 is going to be different from N1 because they have different numbers of lone pairs and bonds, so their formal charge is going to be different. So for this nitrogen, it still has 5 valence electrons. That is a consistent thing for all of our elements since we get that from the periodic table, not from the structure. For lone pairs, it has 1, 2, 3, 4, 5, 6 electrons in lone pairs. And for shared electrons, it has 1, 2 electrons that are in a bond, which we divide by 2 because they're shared, and we simplify that to 1. So we have 5 minus 6 minus 1, so essentially 5 minus 7. So that gives us a total charge of minus 2. So the formal charge on nitrogen 2 is minus 2. We can double check our work. The N2O that's given in the problem is neutral. So it has a charge of 0. So our formal charges overall are 0 plus 2 minus 2. That's an overall charge of 0. So we checked our formal charges and they equal out to 0, which is neutral on the molecule. So we are good. Okay. Try this next one. This is the NO2 plus ion. So again, we have to account for our charge there when we're doing this formal charge calculation. It's very similar in structure to our previous atom. Okay, instead of N2O, we have NO2. Okay, so what I want you to do is pause the video. I'll have my work shown here so you can utilize it to help you. Okay, try this molecule and determine the formal charge for each atom in that molecule. Try that one on your own. Okay, see how far you get. If you get stuck, feel free to come back to the video and we'll work through it together. Let's label our oxygens so we know we're doing the right ones. We have O1 and O2. So we'll start off, we'll go left to right, we'll do O1 first. Oxygen, we know, has 6 valence electrons. In this structure, it has 2 electrons that are in lone pairs. And it has 1, 2, 3, 4, 5, 6 electrons from bonds that we're going to divide by 2 and simplify to 3. So we have 6 minus 2 minus 3, so that gives us an overall charge of plus 1. Okay, for oxygen number 2, we have 6 valence electrons. It has no lone pairs, just like our previous example. And it has 1, 2, 3, 4, 5, 6, 7, 8 electrons in bonds, which we divide by 2 and simplify to 4. So this has an overall charge of +2. You'll notice between our two structures here, this oxygen had 4 bonds with no lone pairs, and so did that oxygen. So even though what it was attached to is different in this structure, it still has the same formal charge. So we can make that same assumption for our nitrogen here on the end. In this previous problem, we said, well, if it has 6 electrons in lone pairs and 1 bond, then it's going to have an overall charge of -2. They look the exact same. The calculation works the exact same in the same way the oxygen calculation did. Okay? Because these electrons, they're just numbers, right? They're just individual, we count electrons 1, 2, 3, 4. So if it has 6 valence electrons and 1 bond, its number of associated electrons is still the same. So we can deduce that this nitrogen has a -2 charge because it works out the same way as we did in our previous problem. So if we add up all of our formal charges, we have +1, +2, -2. That gives us a final charge of +1, which equals the charge of +1 on this molecule. So we are good. Let's keep practicing. Let's try this one. So this is H3O+. This ion has a special name that we're going to learn about throughout this semester. This is called hydronium. The hydronium ion. Okay, H3O+. So try to find the formal charge for each of these atoms. Our hydrogens our hydrogens are all the same, so we can find the formal charge of 1, meaning we know the formal charge of all of them. Hydrogen has 1 valence electron. It has no lone pairs. And it has 1 bond that has 2 electrons in it. So we take 2 electrons from bonds, divide that by 2, which simplifies to 1. So overall, the formal charge of hydrogen becomes 1 minus 0 minus 1. So the formal charge on each of these hydrogens is 0. Okay, so let's try oxygen then. Hopefully our oxygen has a charge of +1 to match our +1 charge on this molecule. So, we know that oxygen has 6 valence electrons. It currently in the structure has 2 electrons that are wrapped up in lone pairs. And it has 1, 2, 3, 4, 5, 6 electrons that are currently in bonds. So 6 electrons from bonds, which we divide by 2 because they're being shared. And 6 divided by 2 simplifies to 3. So our overall formal charge for that oxygen is 6 minus 2 minus 3, so 6 minus 5, which equals +1. So the formal charge on this oxygen is +1. If we add up all of our formal charges, +1 plus 0 plus 0 plus 0, that equals +1, which matches the charge of our ion. Okay. Let's do a few more where we first draw out our Lewis structures and then determine our formal charges, because for a lot of our Lewis structures, for a lot of our formal charges, we have to determine our Lewis structure first. And if we don't have the right Lewis structure, then we won't have the right formal charge. So take a second and pause your video and first draw out the Lewis structures for each of these ions using our rules from our previous lesson. If you're confident in your skills of formal charge, feel free to try to determine the formal charges on your own and then use the videos to check your work. If you're still not as confident, that's totally fine. Draw your Lewis structures first, come back to the video, and work through the formal charges with me. For our first example, S2, 2 minus, we have a total number of 14 electrons to work with. That comes from 2 times 6 from the sulfur plus the 2 electrons that are extra in our charge. Okay, our charge is 2 minus, so therefore we need to account for 2 extra electrons. So in our structure, we have S bonded to S, so that used up 2 electrons. I now have 12 left over that I'm going to use and put on as lone pairs. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, that used up all 12 of my electrons that are left over. And I'm going to put my bracket around here to put my 2 minus on the outside to show that it is an ion. Each sulfur is the same, so we're going to find just the formal charge of one sulfur and we can apply it to the other. So sulfur has 6 valence electrons. Each sulfur has 1, 2, 3, 4, 5, 6 electrons in lone pairs. And each sulfur has 1 bond, which has 2 electrons. So we're going to subtract off our 2 electrons from bonds, but divide it by 2 since they're being shared. That simplifies to 1. So 6 minus 1 is a -1 charge for each of these sulfurs. If we add up those 2 charges, -1 and -1, we get -2. Okay, let's move on to our next one. Our structure for BrF3 or F2 plus is BrF with some lone pairs on the bromines and the fluorines. Everyone has an octet and is happy, and we have a charge of a positive. If your Lewis structure does not look like that, please make sure that you accounted for all of your valence electrons in this ion, specifically remembering to subtract off 1 from that plus charge. Okay, each fluorine is going to have the same formal charge, so we just need to find it for 1 and then the bromine. So our fluorine has 7 valence electrons, currently has 6 electrons in lone pairs, and has 2 electrons that are in bonds, which we divide by 2, which simplifies to 1. So 7 minus 6 minus 1 is a formal charge of 0, so the formal charge on each fluorine is 0. Our bromine here, bromine again has 7 valence electrons, just like fluorine. It has 4 electrons in lone pairs, and it has 4 electrons in bonds, which we divide by 2, simplifies to 2. 7 minus 4 minus 2 is plus 1. So that bromine has a charge of plus 1. So our overall charge is plus 1, which corresponds with our charge of the molecule. Okay. Okay, let's do our last example here. For our Lewis structure for this one, we get S single bond C single bond N with lone pairs on the nitrogen and the sulfur. Okay. We need to complete our octet for our carbon, and so what we're going to do is we are going to donate our 2 lone pairs from nitrogen, and we'll see why in a second. SC triple bond N with a lone pair, and sulfur with lone pairs. Now I chose to do my lone pairs from nitrogen because in my final structure here, oops, I forgot my charge. In my final structure here, my nitrogen has 1 lone pair and 3 bonds, which if you remember from our previous lesson about our rules for specific atoms, nitrogen prefers to have 3 bonds and 1 lone pair. So this structure is the one that would then follow those rules of our individual atoms of nitrogen. So that's why I chose to move 2 of my lone pairs from nitrogen onto the carbon instead of taking any from sulfur, because there are no specific rules for sulfur, at least not for right now. We may learn about some in our next section, but for right now, nitrogen is the one that has the rule about it. Okay, so let's do our formal charges. Let's see. We have sulfur first. Sulfur has 6 valence electrons, currently has 6 electrons in lone pairs, and has 2 electrons in bonds, which we divide by 2 and simplify to 1. So 6 minus 1 is an overall charge of -1 on the sulfur. Our carbon is next. Carbon has 4 valence electrons. It has no electrons in lone pairs. And it has 8 electrons in bonds, which we divide by 2 because they're shared and simplify to 4. So 4 minus 4 is 0. The overall or the formal charge on the carbon is 0. Next up, we have nitrogen, which I'm going to move all the way over here. Sorry, I don't have enough room. Nitrogen has 5 valence electrons, currently has 2 electrons in lone pairs, and 6 electrons in bonds, which we divide by 2 because they're shared. That simplifies to 3. 5 minus 2 minus 3 is a charge of 0. So our formal charge of nitrogen is 0. If we add up all of those, we get -1, which is the charge on our molecule. Okay, a little messy, but still the same steps on each atom. You have to find each of the formal charges individually. When you are drawing Lewis structures and it tells you to identify the formal charge, this is where instead of putting the charge on the outside, we can now show where the electrons are specifically localized. So for a structure like S, C, and N, we have all of our lone pairs here. So instead of putting a bracket around this, I would actually put a charge of minus directly on my sulfur, or as close as I can get to the sulfur, because that's the atom that has the -1 charge that's contributing to the overall charge of -1. For something like the BrF2, we would show it as F, Br, F, lone pairs, some lone pairs on the Br, and since the bromine had the +1 on it, we would put the plus right on the Br instead of putting it in brackets. And for the sulfurs, they would just go on each sulfur. Okay, so when you're working on your ALEKS homework and it tells you to draw Lewis structures and reminds you to account for formal charge, when it asks you to do that, it wants the charge on the specific atoms that have formal charges. Okay, so let's move on. Now that we know how to draw Lewis structures, figure out the formal charge for each atom in the Lewis structure, okay, we can now talk about some of our exceptions to the octet rule. Now, we've seen many exceptions to many of our concepts so far in our lessons, so of course we're going to have some exceptions to our octet rule. So remember, our octet rule is everything wants 8. That's again, 8 is great. Oops. Helps if I could spell great. But with our exceptions, we're going to see that not 8 is also great. So sometimes we're going to have more or less than 8. So when drawing Lewis structures, up until now we have been obeying the octet rule. However, with many topics we've seen up till now, there are exceptions. So we have 3 different exceptions to our octet rule. So those are 3 different categories. Our first exception is a version of an incomplete octet. Where the central atom has fewer than 8 electrons due to a shortage of electrons. Okay, a shortage of electrons. This we typically see in elements early in the periodic table. So I have the example here of beryllium. We see it with hydrogen as well. Hydrogen, we know, only makes 1 bond to have 2 electrons, so it doesn't obey the octet rule. Okay, we have the example of beryllium here. If we look at how to draw our Lewis structure of BeH2, well, beryllium has 2 valence electrons plus the 2 valence electrons from the 2 hydrogens. I only have 4 electrons to work with, so I don't even have enough electrons to create an octet. So my 4 electrons are strictly going in making those bonds. So I just don't have enough electrons to complete my octets. So we only see this in elements that don't have enough electrons. So this would specifically be hydrogen, lithium, beryllium, and boron, as well as aluminum. Okay, so those are the elements that we typically see this in. Not every element can have a shortage of electrons. If you have extra electrons from your counting, then you have to put them into the structure. You can't just throw them away. So this is specific for these 5 elements. So let's prove this. Let's just double check that we can prove this with our compound boron trichloride. So we have to practice our naming here. Boron on our periodic table is B. Trichloride, well, we know chloride is chlorine, so that'd be Cl, and the tri means 3, so BCl3, boron trichloride. So we take our valence. Boron has 3 valence electrons, it's in group 3, plus the 3 times the 7 from the chlorine. Okay, so that gives us a total of, what's that? 24 electrons to work with. So I have some electrons to work with. So let's see. We next follow up with our steps. Boron is in the middle. It's bonded to the 3 chlorines. I used up 6 electrons to do that, and I have 18 electrons left over. My next step says to complete my octets. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Minus 18 electrons to give no electrons left over. Now, boron does not have an octet, but if we remember our rules, halogens don't like more than 1 bond. And this is typical, this is a general overview of halogens. We're going to see some exceptions to that as one of our exceptions to our octet rules, but if we can avoid it, then that's fine. And the reason why we're able to avoid it is because boron it has an incomplete octet. Okay, I have no electrons left. Boron just strictly will not form any double bonds. This is because it's so small, it only has 5 protons. So if I tried to make any double bonds or anything like that, it's just overloading that nucleus with too many electrons, and it doesn't balance out the charges very well. So boron is fine having only 3 bonds. We also see this with, BH3, where I only have 6 electrons to work with. So BH3 looks like this. I use up all 6 of my electrons, making the structure, making the bonds, but this is an acceptable structure because I just don't have any electrons left over. Okay, so boron is one of those that is fine having an incomplete octet. Our next exception is again another version of an incomplete octet. But it's specifically where we have, where the central atom has fewer than 8 electrons because it has an odd number of electrons overall. So we've looked at a lot of Lewis structures so far, and all of our valence electrons that are contributing to bonding have always been even, and if they were odd, we usually had a charge that would change that. But in some cases, like the example of just NO2 without a charge, okay, we have for our valence electrons 5 from the nitrogen plus 2 times 6 from the oxygen. That's a total of, what's 12 plus 5? 17? 17 electrons total. So if we look at the electrons in this structure, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So I've accounted for all 17 electrons. I've followed my rules for bonding in this structure. Okay, my rules for Lewis structures here. But I just have an odd number of electrons in my total number of electrons. So 1 electron just won't be paired up. So that's the 1 electron on the nitrogen. A molecule that has an odd number of electrons are referred to as free radicals. So this specific exception is referred to as the free radical exception, where we have an odd number of electrons. It's still an incomplete octet because the nitrogen only has 1, 2, 3, 4, 5, 6, 7 electrons. But it's because of an odd number of electrons, not because I didn't pair my electrons up correctly. And that's called a free radical. So we don't see these often. They are very rare, okay, because electrons really do prefer to be paired up. So if we have a case where we have 1 electron that's unpaired, it will typically be removed, and that's how we get an ion. So another version of this that we've seen in this lecture was NO2 plus, where we saw the structure for that, and it didn't have a free radical. So typically we don't see free radicals that often, so just keep that in mind. Okay, the most common exception is our last one, and this is a central atom that has more than 8 electrons, and this is called an expanded octet. So it has more than 8, expanded. This can go up to 10 electrons or 12 electrons. It will not go any further. Okay, so 10 electrons or 12 electrons around the central atom. That's where it stops. It's not going to go any further. It's not going to have 14, 16, 25. It's not going to have any more than 12 electrons. Okay, so it's either 10 or 12 electrons around the central atom. Okay, so here we have SF6. Okay, sulfur hexafluoride. And we can see that because there's 6 fluorines, I have to accommodate them somehow. We know that fluorines only like to make 1 bond, so the only way that we can do that is put all 6 of those fluorines on the central sulfur. Okay, so the sulfur now has to accommodate 6 bonds corresponding to 12 electrons around it. So it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons around it. So expanded octets mean that they have more than 8 electrons. And this only happens in atoms that are in and beyond the 3rd period. Okay, so everything from period 3 down. So this is going to be sulfur, phosphorus, chlorine, selenium, bromine. Let's see, let me write some of these down. Sulfur, phosphorus, chlorine, selenium, bromine, iodine. We can even have the noble gases getting in on this. Okay, they can now form expanded octets. Okay, so, and this is because everything in group 3 has access to a 3d orbital that they can utilize to accommodate these extra electrons. So in everything from in row 2, what we were talking about before with the proton or the nucleus being so small, not having a lot of protons, well, as we get a larger and larger nucleus with more and more protons, we can accommodate more electrons, and we accommodate them in the d orbitals. Okay, so that's why these are able to occur. We know that there is no 2d orbital if we look at our orbital chart from back in chapter 4. We could check that, but there is no 2d orbital. It starts at 3d. So because these elements are in row 3 and down, they have 3d and 4d orbitals that they can accommodate the extra electrons in. Okay, so let's look at a few of these. So let's follow our Lewis structure rules and draw the Lewis structures for the following compounds, and then determine which exception it falls under. So exception 1, 2, or 3. 1 being incomplete octets because there's not enough electrons, 2 being incomplete octets for free radicals, and 3 being expanded octets. Okay, so first we have HO2. HO2, let's follow our rules. HO2 has 1 valence electron from the hydrogen, and then there's 2 oxygens which each have 6, so we have 13 electrons total. So our structure becomes H, O, and O, right? H can't be our central atom, so oxygen will be. So that oxygen will have 1 oxygen and a hydrogen bound to it. So I used up 4 electrons to do that. That leaves me with 9. So I'm going to fill in my octets. So hydrogen is good. I'm going to do my oxygen out here first because it's my surrounding atom. I used up 6. I have 3 electrons left. They go 1, 2, 3, which means I have no electrons left over. So since I've been dealing with odd numbers, I had an odd number of electrons here in my count. We know that this is going to be exception number 2. The incomplete octet with a free radical. So we have this 1 electron that's unpaired. So that's a free radical there. So if you see an odd number of electrons, they're not going to pair up because you don't have enough electrons. So it'll automatically be an incomplete octet with a free radical. Okay, let's do our next one. Al-I3. Aluminum is in group 3, so it has 3 valence electrons. And then I3, there's 3 iodines, each have 7 electrons around them. So that is 24 electrons total. We have Al with an I on each side. So that used up 6 electrons. I have 18 left over. I'm going to use those to complete my octets of my iodine. So I used up all 18. I have no electrons left, and because aluminum is in group 3, it is fine with exception number 1. an incomplete octet. With too few electrons. I just don't have enough electrons. And I'm not going to form any multiple bonds because the halogens would prefer not to form double bonds, and group 3 elements don't prefer to form double bonds either. So that could be another rule that you add to your rules of atoms. Boron and aluminum don't like to make double bonds. They like single bonds. They like 3 single bonds and that's it. Okay, our last example is PCl5. PCl5, phosphorus, has 5 valence electrons. We have chlorine, which is going to be 5. There's 5 of them, and they each have 7. So that's 40 electrons. We have so many electrons. Okay, so phosphorus is in the middle. It's going to bond to chlorines. Okay, I'm going to try to make it as compact as possible. Okay, so I had to make 5 bonds to accommodate all of those chlorines. So that was 10 electrons total. I have 30 electrons left over. I'm going to use those to complete my octets of all of my chlorines. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. I used up all 30 to complete my octets. I already had more than an octet on my phosphorus, so I don't need to worry about that one. So this would be an exception for number 3. An expanded octet. Okay, so those are our 3 structures for our 3 exceptions to our rules. The exception that you are going to see most often is going to be exception number 3, expanded octets. So, for our last set of practice, I want to take some time and practice drawing these Lewis structures for all of these molecules which have expanded octets. So you're going to expect to have more than 8 electrons around the central atom in each of these molecules. So what I want you to do is pause the video, follow your Lewis structure rules for each of these molecules, and try to draw their Lewis structures, each with expanded octets. Following the rules will still result in the expanded octets because you just have so many electrons that you're going to be working with. Okay, so try these on your own and come back to the video to check your work, or if you get stuck, to get unstuck. As we said before, the noble gases start being included when we start talking about expanded octets. So they can start to form structures when they have expanded octets. So if we look at our first example, XeF4, xenon tetrafluoride, we have 8 valence electrons that are coming from the xenon, and there's 4 fluorines, each with 7 valence. So in total, we have 36 electrons to work with in this structure. So we start with xenon in the center, and it's going to bond to 4 fluorines. Okay, so I made 4 bonds with 8 electrons. So I have 28 electrons left. I'm going to use those electrons to complete my octets on all of my fluorines. So that's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. I used 24 electrons to complete my octets, and I have 4 electrons left over. Now, if we follow our rules for Lewis structures, it now says to place any remaining electrons on the central atom as lone pairs. So we're going to take these 4 electrons and put them on xenon as lone pairs. Okay, so we're still following our Lewis structure guidelines, no different for these exceptions to our octets or anything like that. We're still following those guidelines. The guidelines will then allow us to show that we can have expanded octets. So our xenon has an expanded octet because it has 1, 2, 3, 4 bonds, which is 8 electrons total, as well as 2 lone pairs, which is in total 12 electrons around it. So our xenon has an expanded octet with 12 electrons around it. Okay, let's try another one. Let's try selenium tetrafluoride. So very similar to the one that we have right now. Our structure is going to look a little bit different, but selenium tetrafluoride is 6 valence from the selenium and 4 times 7 from the fluorines again, which is a total of 34 electrons. So it's going to look very similar to what we just did. So we're going to have selenium in the middle, 4 fluorines around it. We know that to complete their octets, we have to use, let's see, we used up 8 electrons. We have 26 left. To complete the octets of the fluorines, we needed to use 26. Or sorry, 24 electrons. I used up 24 electrons to complete the octet. I have 2 electrons left over, so those 2 electrons are going to go on my central atom of selenium as a lone pair. So still following those rules, 1, 2, 3, all the way through to the end. With expanded octets, though, we are not going to be forming multiple bonds. No multiple bonds. We've already surpassed our octets. We don't need to form multiple bonds because the rules tell us, our very last rule is, if octets are not complete. Well, with expanded octets, the octets are complete with some extra electrons in there. So we don't need to make any double or triple bonds. So we will not see any double bonds in here or triple bonds or anything like that. So don't think that this lone pair now needs to go onto here to make a double bond. It won't happen because our rules, again, are halogens prefer not to have double bonds. Okay, so when we're having expanded octets, we do not form multiple bonds. Our last example is XeOF4. So very similar to what we did in our last 2 examples now, but we now have an oxygen thrown in there, so that's going to change a few things. So let's count. Xenon has 8, oxygen has 6, fluorine again has 4 times 7. That is a total of 42 electrons. That's a lot of electrons. Let's draw it over here on the side. We have xenon in the center. Now we're going to have an oxygen and then our 4 fluorines. I'm going to do a fluorine here. 1, 2, 3. How am I doing this? 1, 2, 3, 4. There we go. I can fit all of them. Fitting all of these with an expanded octet takes a little bit of practice. Okay, so I made 5 bonds, so I used up 10 electrons. So we then subtract off 32, or so we're left with 32. I'm now going to use my extra electrons to complete my octets. So I'm going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So I used 30 electrons to complete my octets. I have 2 left over, which I'm going to put on my xenon because it can have an expanded octet. So that is our final structure for xenon. Xenon with an oxygen and 4 fluorines. No specific name for that, at least for the place that we're at right now. Okay. So if we look at this, if you look at this structure, you may think, okay, well, the fluorines are following our rules, halogens only making 1 bond, but oxygen is not following its rule. But if I were to try to move one of these, because oxygen prefers to have 2 bonds and 2 lone pairs, if I tried to do that, that would create a multiple bond in my structure. But with expanded octets, there are no multiple bonds. At least for what we're doing. Are there exceptions to that? Sure, there's exceptions to everything. But for what we are learning about, we will not have any multiple bonds forming with these expanded octets. Okay. So that completes our lesson on Chapter 6, our second lesson of Chapter 6, where we talked about formal charges and exceptions to our octet rule in Lewis structures. So, before you move on to your next chapter or your next exam, please make sure that you finish the ALEKS homework and master the concept of formal charge and expanded octets, or exceptions to the octets, before moving forward.